Hello everyone, today I'll be talking about the operation principles of mobile phones. The operation principles of mobile phones. The operation of a mobile phone is based on a combination of several technologies including cellular networks, radio waves, digital signal processing and various sensors. Here are the key principles behind its operation. The first here is cellular network communication. Mobile phones rely on a network of base stations, that is cell towers, to connect and transmit information. These networks are divided into cells, each served by a tower with a specific range. The phone communicates with the nearest base station via radio waves. Base stations. Base stations are towers responsible for sending and receiving signals from nearby phones. They relay calls and data to the broader telecommunications network. And then we'll talk about handoff. When a mobile phone moves from one cell to another, the system transfers the connection to the next tower to maintain the signal, known as handoff. Number 2, radio waves. Mobile phones use radio frequency signals to send and receive data. Different frequency bands like 3G, 4G or 5G are allocated to carry voice and data. Duplex communication. Phones use two frequencies to allow two-way communication, one for sending and one for receiving signals, allowing you to talk and listen simultaneously. The third is digital signal processing. When you speak into a mobile phone, your voice is converted into digital signals through a process called sampling. The mobile phone uses a codec to compress these signals, which are then transmitted as small data packets. First under here, we consider analog to digital conversion, ADC. The microphone converts sound waves into electrical signals, which are digitized. Next, we consider data compression. The digital signal is compressed to reduce bandwidth usage, and we also consider error correction. Algorithms are used to correct errors caused by noise in the transmission process. Number 4 is modulation techniques. The digital data is then modulated onto a carrier wave, which is usually a high frequency signal, to be transmitted over the air. Techniques like frequency division multiple access, time division multiple access, or code division multiple access are used to allow the multiple users to share the same frequency. Number 5, receiving and demodulation. When the mobile phone receives a signal from the network, the process is reversed. The signal is then demodulated, error corrected and decoded back into the original audio or data stream. Another key point in the operation principles of mobile phones is power management. Mobile phones are equipped with battery management systems that control the usage and charging of the battery, ensuring efficient use of power. Low power modes are often used to save battery life when the phone is idle. Number 7, sensors and microcontrollers. Modern smartphones are packed with sensors such as gyroscopes, accelerometers, GPS and so on that gather data about the phone's environment. Microcontrollers process this data, allowing the phone to provide advanced features like location services and orientation detection. The 8th principle is operating system and apps. The software, which is the operating system of a mobile phone, manages its hardware resources and provides a platform for applications. The operating system handles memory, storage, networking and user interfaces, enabling multitasking and running apps. In summary, a mobile phone operates by converting voice and data into digital signals, transmitting them wirelessly through a cellular network, and using various protocols and techniques to ensure the efficient and reliable delivery of information. Now we are going to consider all these 8 principles one by one. The first is cellular network communication. This is the backbone of mobile phone operations. It allows mobile phones to connect with each other and access the internet wirelessly. Here is a breakdown of how it works. Number 1. Cellular network structure. The core concept of cellular networks is to divide a geographic area into smaller regions called cells, each of which is served by a base station or cell tower. These cells provide coverage to ensure continuous communication across the entire area. Let's consider some points under this. Number 1 is cells. Each cell represents a geographic area covered by a single tower. Cells are typically hexagonal in design to maximize coverage and minimize interference with neighboring cells. The next is base stations. Each cell contains a base station that consists of antennas and radio transceivers. These base stations manage communication within the cell, linking mobile phones to the core network. Number 2, mobile phone and base station interaction. When you turn on a mobile phone, it establishes a connection with the nearest base station using radio waves. The phone communicates with the base station through an exchange of signals. Let's consider some points under here. The first is signal strength. The mobile phone continually measures the strength of signals from nearby base stations. It connects to the one with the strongest signal, usually the closest. Next is handoff or handover. As the phone moves from one cell to another, such as when you are in a car, the network seamlessly transfers the connection to a new base station to maintain communication. This process is called handoff. Number 3, frequency bands and multiple access. Frequency bands and multiple access. To allow many users to share the same network infrastructure, cellular networks use frequency bands and multiple access techniques. The first I'm going to consider is frequency division multiple access. Different users are assigned different frequency bands within the cell to avoid interference. We also have the use of time division multiple access, where different users share the same frequency band but transmit in different time slots. Next is the code division multiple access, where users are distinguished by unique codes, allowing them to share the same frequency simultaneously without interfering with each other. We also have orthogonal frequency division multiplexing used in 4G and 5G. It splits the frequency spectrum into many smaller channels, each carrying a portion of the data. This improves data rates and signal robustness. Number 4, core network or backhaul. Once the base station receives a signal from a mobile phone, it forwards the signal to the core network, which consists of several components. First is mobile switching center. This is the central hub that connects base stations to each other and routes voice calls between different parts of the network or other networks, such as in landlines. Next is gateway. For internet access, the core network has gateways that connect to the internet, allowing mobile phones to access online services like browsing, streaming, or using apps. We also have home location register and visitor location register. These are databases that store information about subscribers, such as their location, subscription details, and they also manage roaming services. Number 5, data and voice transmission. Mobile networks support both voice and data communication. In modern networks, data is transmitted using packet switching technology, while voice calls are either circuit switched or packet switched. Let's consider packet switched networks. Here, data is split into small packets and transmitted over the network. These packets are routed independently and reassembled at the destination. The other one is circuit switched networks. A dedicated communication path or circuit is established between the caller and the receiver, which is maintained for the entire duration of the call. We also have voice over LTE and voice over IP. In 4G and 5G networks, voice calls are transmitted as data packets, improving the quality of call and also the efficiency. Number 6, generation of cellular networks. There are several generations of cellular network technologies, each with its own improved capabilities and speed. The first is 1G, which is analog. The first generation networks used analog signals for voice communication. Then next we have 2G, which includes GSM and CDMA. These introduced digital signals for voice, adding features like text messaging and low-speed data. Then we have the third generation, 3G. Examples are UMTS, HSPA, CDMA 2000. This generation enabled faster data transfer for mobile internet, video calls, and multimedia messaging. Then next we have 4G. Examples are LTE and LTEA. This supports high-speed data transfer for HD video streaming, VoIP, and faster internet services. And we also have 5G, which provides us ultra-fast data transfer speeds, low latency, and supports a massive number of connected devices, making it ideal for Internet of Things, autonomous vehicles, and enhanced mobile broadband. Another key point under cellular network communication is roaming. When a mobile phone moves outside its home network's coverage, it can still communicate by connecting to a foreign network through a process known as roaming. The home network collaborates with the foreign network to provide service, allowing users to make calls and use data internationally. Number 8 under cellular network communication is security and encryption. Cellular networks use encryption protocols to protect communications from eavesdropping. Data is encrypted at both the user's phone and the base station, ensuring privacy during transmission. In summary, cellular network communication involves the coordination of base stations, frequency allocation, and data handling within the core network to ensure mobile phones can communicate seamlessly over long distances, across borders, and between different types of services like voice and data. Let's now move to radio waves. Radio waves are fundamental to mobile phone communication, enabling the wireless transmission of voice, data, and other forms of information between the mobile device and the cellular network. Let's have a look at how they are used in mobile phones. What are radio waves? Radio waves are a type of electromagnetic radiation. They are part of the electromagnetic spectrum and travel at the speed of light. They are used for wireless communication because they can carry information over long distances and penetrate obstacles like walls and buildings. They can carry information over long distances and they are able to penetrate obstacles like walls and buildings. Number 2, frequency bands in mobile phones. Mobile phones operate using specific frequency bands that are allocated by regulatory authorities. Different generations of mobile networks such as 2G, 3G, 4G, and 5G use different ranges of frequencies for communication. These frequencies are measured in hertz. For the second generation networks such as GSM, they operate typically in 900 MHz and 1800 MHz bands. For the third generation networks such as UMTS, they use frequencies in the 850 MHz, 900 MHz, 1900 MHz, and 2100 MHz bands. For the 4G networks, they operate in a wider range of frequencies from 700 MHz to 2600 MHz. 4G networks have a wider range of frequencies ranging from 700 MHz to 2600 MHz. And for 5G networks, they use frequencies from sub-6 GHz band such as 3.5 GHz to high-frequency millimeter waves like 24 GHz and above for faster speeds and lower latency. Number 3, transmission of information via radio waves. Radio waves carry information by modulating the wave's properties such as amplitude, frequency, or phase. These modulation techniques are used to encode the voice or data being transmitted. Let's have some common modulation techniques. The first is frequency modulation. This changes the frequency of the wave to encode the information. We also have amplitude modulation, which alters the amplitude, that is the strength of the wave, to transmit data. And we have phase modulation, which modifies the phase of the wave to encode information. The phase modulation modifies the phase of the wave to encode information. Number 4, uplink and downlink. In mobile communication, radio waves are used for both uplink, that is when the phone sends data to the network, and downlink, that is when the phone receives data from the network. The first, uplink, phone to tower. The phone sends signals such as voice or data to the nearest base station using radio waves. And we have downlink also, that is from tower to phone. The base station transmits signals back to the phone, allowing the user to receive calls, text, or data. Uplink is when the phone is sending signal to the nearest base station using radio waves, while downlink is when the base station is transmitting signals back to the phone, allowing the user to receive calls, text, or data. Number 5, duplex communication. Mobile phones use duplex communication, meaning they can send and receive signals at the same time. This is accomplished using different frequencies for uplink and downlink, ensuring that the two don't interfere with each other. This involves number 1, frequency division duplexing, where different frequencies are used for uplink and downlink. It also involves time division duplexing, where the uplink and downlink share the same frequency but are transmitted at different times. Number 6, signal strength and interference. The strength of the radio wave signal affects the quality of the mobile connection. A strong signal typically means clearer voice calls and faster data transfer, while a weak signal can result in dropped calls or slow internet speeds. Signal strength depends on factors such as number 1, distance from the cell tower. The further the phone is from the base station, the weaker the signal. Number 2, obstacles. Buildings, terrain, and other obstacles can block or weaken radio waves. Number 3, interference. Other electronic devices, physical structures, or environmental factors can cause interference, leading to signal degradation. Number 7, radio wave propagation. Radio waves can propagate in different ways depending on their frequency and the environment. Under here, we shall consider first line of sight. Higher frequency waves, such as those used in 5G millimeter waves, travel in straight lines and require a clear line of sight between the phone and the base station. Number 2 here is reflection and refraction. Lower frequency waves, such as those used in 2G, 3G, and 4G, can reflect off buildings or bend around obstacles, allowing for communication even when the phone is not in direct line of sight with the tower. And third, we have diffraction. Waves can bend around obstacles such as hills or buildings, improving coverage in areas with physical obstructions. Number 8, antenna design. Both the mobile phone and the cell tower use antennas to transmit and receive radio waves. The efficiency of these antennas plays a crucial role in the strength and quality of the signal. The first here is phone antenna. Modern smartphones have internal antennas that are designed to be small but efficient across multiple frequency bands. These antennas switch between frequencies based on the network, such as 2G, 3G, 4G, or 5G. We also have cell tower antennas. Towers are equipped with directional antennas that focus signals towards specific areas, also known as cells, reducing interference and improving coverage. Reducing interference and improving coverage. Number 9, health and safety. There are regulations governing the power and frequency of radio waves used by mobile phones to ensure safety. Mobile phones emit non-ionizing radiation, meaning they do not have enough energy to ionize atoms or molecules, unlike X-rays or gamma rays. However, studies are ongoing to ensure there are no adverse health effects from long-term exposure to radio frequency radiation. Number 10, spectrum sharing and efficiency. Spectrum sharing and efficiency. Mobile networks must efficiently manage the use of radio waves to accommodate millions of users. Techniques like number 1, carrier aggregation, which combines multiple frequency bands to provide faster data rates. Number 2, spectrum reuse, allowing multiple users in different locations to use the same frequencies without interference. These techniques optimize how the limited spectrum is used for the growing demand for mobile communication. The techniques optimize how the limited spectrum is used for the growing demand for mobile communication. In summary, radio waves are essential for mobile phones to wirelessly transmit and receive information. They carry signals over specific frequency bands, modulate data, and allow for real-time communication, whether through voice calls, text messages, or internet access. They carry signals over specific frequency bands, modulate data, and allow for real-time communication, whether through voice calls, text messages, or internet access. Number 3, digital signal processing. Digital signal processing plays a critical role in mobile phones, enabling them to handle voice, data, and multimedia efficiently. Digital signal processing converts analog signals like voice into digital signals for transmission and vice versa. Let's have a look at how digital signal processing works in mobile phones. Number 1, signal conversion. Mobile phones primarily deal with analog signals such as sound waves and must convert these signals to digital form for processing, transmission, and storage. The digital signal processing handles this conversion. Let's consider under here analog to digital conversion, ADC. The microphone captures sound, which are analog signals, which is then sampled at regular intervals and converted into digital data, that is bits. This digital representation can then be processed or transmitted by the phone. And then next we consider digital to analog conversion, DAC. When receiving data, the digital signal processing converts the digital signals back to analog form, such as sound played by the speaker or earphones. Number 2, data compression. Raw digital signals such as voice or video contain a lot of redundant information. The digital signal processing reduces the size of this data using compression algorithms without significantly affecting the quality. Compression is crucial for reducing bandwidth usage and ensuring efficient transmission over mobile networks. Under here we shall consider lossy compression. For audio, algorithms like MP3 or AAC are used to reduce file sizes by removing inaudible parts of the signal. And then we also have lossless compression. In some cases, lossless compression is used where no data is lost during compression and decompression, though this is less common for voice or video due to larger file sizes. Number 3, error detection and correction. During transmission, signals can become corrupted due to interference, noise, or signal fading. The digital signal processing includes error detection and correction mechanisms that identify and fix errors in the received data. This could involve error detection. Techniques like cyclic redundancy check help identify if an error has occurred in the transmitted data. It could also involve error correction. Algorithms like forward error correction allow the receiver to correct certain errors without needing retransmission. Number 4 is modulation and demodulation. To send data over radio waves, the digital signals must be modulated onto a carrier wave, such as a high-frequency signal used in mobile networks. Digital signal processing modulates the digital signal by altering the carrier wave's properties, such as amplitude, frequency, or phase. At the receiving end, the digital signal processing demodulates the signal to extract the original digital data. Under here, I shall consider digital modulation techniques. Techniques such as quadrature amplitude modulation or phase shift keying are used to encode data onto radio waves efficiently. And also we have demodulation. The digital signal processing extracts the digital information from the modulated carrier wave after receiving it. Number 5, noise reduction and signal filtering. Noise reduction and signal filtering. The digital signal processing plays a crucial role in improving the quality of voice and data by removing unwanted noise and interference from signals. Under here, I shall consider noise reduction. The digital signal processing uses filters and algorithms to minimize background noise during voice calls, improving the clarity of conversations. We also have echo cancellation to eliminate echoes in calls where the speaker hears their own voice delayed. The digital signal processing processes the incoming and outgoing signals to remove this feedback. We also have signal filtering. The digital signal processing uses techniques like low-pass filters to remove high-frequency noise from the signal and high-pass filters to eliminate low-frequency noise. Number 6, voice and audio processing. The digital signal processing is responsible for handling voice encoding, decoding, and enhancement. It uses voice codecs like AMR, which means adaptive multirate, for voice calls to compress and decompress speech data, ensuring efficient use of bandwidth while maintaining call quality. I consider under here voice activity detection. The DSP can detect when the user is speaking and only transmit speech data during these moments, conserving the bandwidth. We also have speech enhancement. The DSP, which means digital signal processing, improves speech quality by using algorithms that emphasize voice over background noise. Number 7, multimedia processing. Mobile phones use the DSP to handle multimedia tasks such as video playback, audio streaming, and image processing. This ensures smooth playback and efficient use of resources. Under here, I consider audio processing. The DSP decodes compressed audio formats like AAC or MP3 and applies effects such as equalization and dynamic range compression. Video processing. Video codecs like H.264 or H.265 use DSP to encode and decode video streams, ensuring efficient streaming and playback of videos. We also have graphics and image processing. DSP also aids in processing images for tasks like real-time camera adjustments, applying filters, or compressing image files. Number 8, power efficiency. DSP systems are optimized to perform intensive signal processing tasks while minimizing power consumption. Mobile phones rely on specialized DSP chips to handle tasks that would be too power hungry for the main processor. By offloading tasks like audio decoding or noise cancellation to the DSP, the phone can conserve battery life. By offloading tasks like audio decoding or noise cancellation to the DSP, the phone can conserve battery life. Number 9, equalization and signal shaping. The radio signals used in mobile communication can suffer from distortion and interference due to environmental factors like multipath propagation, where the sound reflects off buildings and reaches the receiver multiple times. DSP uses equalization techniques to counteract these distortions and maintain the quality of the signal. These techniques are: number one, adaptive equalizers, which continuously adjust to changing signal conditions, thus improving the quality of both voice and data transmission. And then number two, signal shaping. This adjusts the transmitted signal to compensate for anticipated losses or distortions, improving overall performance. It adjusts the transmitted signal to compensate for anticipated losses or distortions, thus improving the overall performance. The 10th is multiple input, multiple output, MIMO. In advanced wireless technologies like 4G and 5G, DSP enables MIMO, that is multiple input, multiple output techniques, where multiple antennas are used at both the transmitter and receiver to improve data throughput and signal reliability. Under here we have number one, beamforming. The digital signal processing (DSP) directs radio signals towards specific devices, improving signal strength and reducing interference. We also have number two, spatial multiplexing, which allows multiple data streams to be transmitted simultaneously over the same frequency, thus significantly boosting data speeds. In summary, digital signal processing in mobile phones is essential for converting analog signals to digital, compressing data, modulating signals for transmission, and ensuring the quality and reliability of voice and data communication. Through noise reduction, error correction, and multimedia processing, the digital signal processing enables mobile phones to deliver high-quality voice calls, fast data services, and smooth media playback, all while optimizing power consumption. Number 4, modulation techniques. Modulation techniques are essential in mobile phone communication, allowing data to be transmitted efficiently over radio waves. These techniques modify carrier signals to encode information, enabling the transmission of voice, data, and multimedia content. Here are the primary modulation techniques used in mobile phones. The first is amplitude modulation. In amplitude modulation, the amplitude, that is the strength of the carrier signal, is varied in proportion to the message signal, that is the information being sent. What's the usage? It is primarily used in older analog communication systems. Advantages include simple implementation and easy demodulation, while disadvantages are that they are susceptible to noise and interference, which can degrade the signal quality. The second is frequency modulation. In frequency modulation, the frequency of the carrier signal is varied according to the amplitude of the input signal. What's the usage? It is common in analog audio broadcasts such as FM radio and some digital systems. Advantages are that it has better noise immunity than AM, that is amplitude modulation. It also maintains signal quality over longer distances, while disadvantages are that it requires a wider bandwidth compared to AM, that is amplitude modulation. Number 3, phase shift keying, PSK. It modulates the phase of the carrier signal to represent data. The phase of the carrier is changed to convey different data values. Types are: number 1, binary phase shift keying, which uses two phases, 0 degree and 180 degree, to represent binary data 0 and 1. We also have quadrature phase shift keying, which uses four phases, 0 degree, 90 degree, 180 degree, and 270 degree, to represent 2 bits of data at a time. Advantages are good spectral efficiency and resilience to noise, while disadvantages include more complex receiver design than AM and FM. Number 4, quadrature amplitude modulation QAM. This combines both amplitude and phase modulation, varying both the amplitude and phase of the carrier signal to encode information. The usage is that it is widely used in digital TV and data transmission standards like LTE and Wi-Fi. Types are number 1, 16 QAM, which represents 4 bits per symbol using 16 different amplitude and phase combinations. Number 2, 64 QAM, which represents 6 bits per symbol, offering higher data rates. Number 3, 256 QAM, which represents 8 bits per symbol, further increasing data capacity. Advantages are high data rates and efficient use of bandwidth, while disadvantages are that they are more susceptible to noise and interference, requiring a higher signal to noise ratio. Number 5, orthogonal frequency division multiplexing OFDM. This is a sophisticated modulation technique that divides a high rate data stream into multiple lower rate streams, transmitting them simultaneously over different frequencies. What's the usage? It is standard in 4G LTE, 5G, Wi-Fi and digital broadcasting. Advantages include resilience to multipath interference, efficient spectrum usage, and high data rates, while disadvantages are more complex processing required for modulation and demodulation. Number 6, spread spectrum techniques. Spread spectrum techniques are used to enhance the robustness and security of communications. They spread the signal over a wider bandwidth than necessary. What are the types? Number 1, frequency hopping spread spectrum, which rapidly changes the carrier frequency among many frequency channels. Number 2, we have direct sequence spread spectrum. This spreads the signal across a wider bandwidth using a pseudo random noise sequence. What's the usage? Commonly used in Bluetooth and CDMA cellular systems. Advantages include resistance to interference and jamming, as well as secure communication, while disadvantages are that it requires more bandwidth and can be complex to implement. Number 7, multiple input, multiple output techniques, MIMO techniques. MIMO uses multiple antennas at both the transmitter and receiver to improve communication performance. It employs advanced modulation schemes. Techniques. It combines multiple signals into one, allowing for spatial multiplexing where multiple data streams are sent simultaneously. What's the advantages? Number 1, increased data rates, then improved signal quality and also better coverage. Disadvantages include it requires complex algorithms and hardware. Number 8, pulse amplitude modulation, PAM. In PAM, the amplitude of pulses is varied to encode the information signal. It is often used in digital communication systems. Advantages: it is simple to implement and demodulate. Disadvantages: it is susceptible to noise and interference. In summary, modulation techniques are fundamental to mobile phone communication, enabling efficient data transmission over radio waves. From basic amplitude modulation and frequency modulation to advanced techniques like QAM and OFDM, these methods ensure high-quality voice calls, fast data rates, and robust multimedia communication. Each modulation technique has its advantages and disadvantages, and the choice depends on the specific requirements of the mobile network and application. The choice depends on the specific requirements of the mobile network and application. Number 5, receiving and demodulation. Receiving and demodulation in mobile phones are critical processes that allow the device to convert transmitted signals back into usable information, such as voice, text, or data. This involves several steps, from receiving the radio signals to decoding the data for user consumption. Here is a detailed look at these processes. The first is receiving signals. When a mobile phone is in operation, it constantly scans for radio frequency signals from nearby cell towers. This process involves the following components. Number 1, the antenna. The mobile phone has an internal antenna that receives incoming radio frequency signals. The antenna is designed to operate over a range of frequencies specific to the cellular network standards, such as GSM, LTE, or 5G. We also have the radio frequency front end, the RF front end. The RF front end includes components like filters and amplifiers that help to improve the quality of the received signal. It amplifies weak signals and filters out unwanted frequencies or noise. Number 2, analog to digital conversion, ADC. Once the radio frequency signal is received, it is typically an analog signal that needs to be converted into a digital format for processing. This is done through an analog to digital converter. Under here, I shall consider first sampling. The ADC samples the analog signal at regular intervals to create discrete data points representing the original signal in data form. Another one is quantization. Each sampled value is then quantized, converting the continuous range of values into a finite set of discrete values. The third is demodulation. Demodulation is the process of extracting the original information, such as data, voice, or video, from the modulated carrier signal. The type of demodulation used depends on the modulation technique applied during transmission. Some common demodulation techniques. Number 1, amplitude demodulation. The received signal's amplitude variations are analyzed to recover the original message. Another one is frequency demodulation, where the frequency variations of the received signal are examined to extract the original audio or data. We also have phase shift keying demodulation, where the phase shifts of the received signal are detected to retrieve the encoded data. We also have quadrature amplitude demodulation, where both amplitude and phase variations are analyzed to decode the data transmitted. Next is orthogonal frequency division multiplexing, OFDM. In OFDM systems, the received signal is processed to separate multiple subcarrier signals, each carrying a part of the overall data. This involves number 1, fast Fourier transform, FFT. An FFT algorithm is used to convert the time domain signal into its frequency components. It also involves symbol detection. Each subcarrier is demodulated using appropriate techniques to recover the transmitted symbols. Number 4, error detection and correction. During transmission, data can be corrupted due to interference, noise, or fading. Error detection and correction mechanisms ensure data integrity. Under here, I shall consider some key points. Number 1, error detection. Techniques like cyclic redundancy check or checksums identify whether errors have occurred in the received data. We also have error correction. If errors are detected, algorithms such as forward error correction allow the receiver to correct certain types of errors without needing retransmission. This is often implemented using codes like Reed-Solomon or turbo codes. Number 5, decoding and processing. Once the data has been demodulated and any errors corrected, the next step is to encode the digital data. This involves number 1, voice encoding. If the data is voice, the digital signal is processed using voice codecs such as AMR or AAC to decode it into an audio signal that can be played through the phone's speaker. We also have data decoding. For data packets such as web browsing or texting, the digital data is processed and passed to the appropriate application for display or further action. Number 6, output. Finally, the demodulated and decoded information is sent to the phone's output devices. It involves number 1, audio output. For voice calls, the decoded audio signal is sent to the speaker or earphones. Number 2, display. For data or text messages, the information is rendered on the screen for the user to view. Number 7, feedback and control. Modern mobile phones include sophisticated feedback systems that constantly monitor the quality of the received signals and adjust the receiver settings like gain and filtering to optimize performance. This process helps to maintain call quality and data integrity, adapting to changing conditions such as movement or signal interference. In summary, the processes of receiving and demodulation in mobile phones involve a series of complex steps, from capturing radio signals to converting them into usable information. By utilizing various modulation and demodulation techniques, mobile phones can efficiently transmit and receive voice and data, ensuring seamless communication in a mobile environment. Mobile phones can efficiently transmit and receive voice and data, ensuring seamless communication in a mobile environment. Let's now consider power management. Power management in mobile phones is crucial for optimizing battery life, ensuring efficient energy use, and maintaining overall performance. Given the increasing complexity of mobile devices and the demands of modern applications, effective power management strategies are essential. Here are the key aspects of power management in mobile phones. The first is battery technology. Mobile phones primarily use lithium-ion or lithium polymer batteries due to their high energy density and lightweight properties. Let's consider first battery capacity. It is measured in milliampere hours, mAh, indicating how much charge a battery can hold. Higher capacity generally means longer battery life. We also have here charging mechanisms. Fast charging technologies allow users to quickly charge their devices, often using protocols like Qualcomm Quick Charge or USB power delivery. Number 2, power management integrated circuits. They are specialized chips designed to manage power distribution within mobile devices. They handle various tasks such as number 1, voltage regulation. They ensure that components receive the correct voltage and current. Number 2 is power path management. This determines how power flows from the battery to the device and can manage charging from external sources. We also have here load switching, which controls power supply to different components based on their operational needs. The third is dynamic voltage and frequency scaling. Dynamic voltage and frequency scaling is a technique used to adjust the voltage and frequency of the processor according to the current workload. Under here, I shall consider power efficiency. By lowering the voltage and frequency during light tasks, energy consumption is reduced, extending battery life. Next is performance scaling. During intensive tasks like gaming or video playback, the system can increase voltage and frequency to provide the necessary performance. Number 4, sleep and idle modes. Mobile phones use various sleep and idle modes to conserve power when the device is not in active use. Under here, I shall consider number 1, screen off. When the screen is off, power consumption drops significantly as the display is one of the most power-hungry components. Number 2, app standby. Background applications are put into a low power state when not in use, reducing their resource consumption. And I also have here dose mode for Android. This feature reduces background activity when the device is stationary and not being used, allowing for significant power savings. Number 5. Power consumption monitoring. Mobile operating systems include tools to monitor power consumption, helping users identify apps or services that consume excessive energy. Under here, I shall consider number 1, battery usage stats. Users can see which applications and services consume the most battery, allowing them to manage settings or uninstall problematic apps. Number 2, adaptive battery for Android. This uses machine learning to predict which apps are most likely to be used, and it prioritizes their resource allocation while limiting power to unused apps. Number 6, screen management. The display is one of the largest consumers of power in mobile devices. Effective screen management includes number 1, adaptive brightness. This automatically adjusts screen brightness based on ambient light conditions, helping to save the battery. Number 2, resolution management. Some devices can lower screen resolution during specific tasks to conserve energy. And number 3, OLED technology. Many modern phones use OLED screens where individual pixels can be turned off to save power, especially when displaying dark themes. Number 7, connectivity management. Wireless communication features like Wi-Fi, Bluetooth, and cellular data consume significant power. Power management strategies include number 1, adaptive connectivity. This automatically adjusts network settings based on signal strength and user needs, such as switching between Wi-Fi and cellular data. Number 2, airplane mode. This disables all wireless communications to conserve battery during periods of inactivity or travel. And number 3, low power modes. Certain protocols like Bluetooth Low Energy allow for communication with minimal power usage. Number 8, resource management. Efficient resource management is essential for reducing power consumption. Under here, I shall consider number 1, CPU and GPU management. Offloading tasks to less power-hungry cores in multi-core processors or optimizing graphics processing during gaming can save power. Number 2, background app restrictions. Limiting background activity for certain apps helps to prevent unnecessary battery drain. Number 9, user settings and customization. Users can manually adjust settings to conserve battery life. I shall consider under here number 1, power saving modes. Many devices offer built-in power saving modes that limit performance, reduce screen brightness, and restrict background activity. Number 2, app permissions. Users can control app permissions to limit background processes and reduce power consumption. Number 10, software optimization. Software plays a significant role in power management. Mobile operating systems continuously improve their efficiency through updates and optimizations. Let's consider number 1, app optimization. Developers are encouraged to optimize their applications to minimize battery consumption, such as reducing background processing, using efficient coding practices, and so on. Number 2, system updates. Operating system updates may include improvements to power management algorithms and enhancing overall efficiency. In summary, power management in mobile phones involves a combination of hardware and software strategies aimed at extending battery life while ensuring optimal performance. Techniques such as dynamic voltage and frequency scaling, adaptive screen management, connectivity management, and resource optimization are crucial for maximizing battery efficiency. By effectively managing power consumption, mobile phones can deliver longer usage times and improved user experiences mobile phones can deliver longer usage times and improved user experiences. Number 7. Sensors and microcontrollers. Mobile phones are equipped with various sensors and microcontrollers that enhance their functionality, allowing them to perform a wide range of tasks. These components contribute to user interaction, environmental sensing, and device management. Let's have a look at detailed overview of the key sensors and microcontrollers found in mobile phones. Sensors in mobile phones. Number 1. Accelerometer. What's the function? It measures acceleration forces in 3 dimensions, x, y, z. Uses. Number 1. It detects the orientation of the phone, whether it is portrait or landscape. It also enables motion-based functionalities like step counting and screen rotation. Number 2. Gyroscope. What's the function? It measures angular velocity and orientation. Uses. It enhances motion sensing for gaming and augmented reality applications. It also provides precise orientation data for image stabilization in cameras. The third sensor I'm going to talk about is magnetometer. What's the function? It measures magnetic fields to determine the phone's orientation relative to the Earth's magnetic field. Uses. It serves as a digital compass for navigation applications. It also enhances location accuracy in conjunction with GPS. Number 4. Proximity sensor. What's the function? It detects when the phone is near a user's face. Uses. It turns off the display during calls to prevent accidental touches. It also helps in managing power consumption by turning off the screen when not in use. It turns off the display during calls to prevent accidental touches, as well as helps in managing power consumption by turning off the screen when not in use. Number 5. Ambient light sensor. The function. It measures the intensity of ambient light. The uses. It automatically adjusts screen brightness based on environmental lighting conditions. It also enhances battery life by reducing screen brightness in low light situations. It automatically adjusts screen brightness based on environmental lighting conditions, as well as enhances battery life by reducing screen brightness in low light situations. Number 6. Fingerprint sensor. What's the function? It captures fingerprint data for biometric authentication. The uses. It provides secure access to the device and applications. It also enhances user convenience for unlocking the phone. It provides secure access to the device and applications, and also enhances user convenience for unlocking the phone. Number 7. Camera sensors. What's the function? They capture images and videos using a combination of light sensors. How about the uses? They enable photography, video recording, and various imaging features such as portrait mode and night mode. They also support augmented reality applications through depth sensing. They enable photography, video recording, and various imaging features, and they support augmented reality applications through depth sensing. Number 8. Temperature and humidity sensors. What's the function? They measure environmental temperature and humidity levels. The uses. They provide weather information and alerts. They also enhance functionality in health monitoring apps. They provide weather information and alerts, as well as enhance functionality in health monitoring apps. The 9th sensor I'm going to consider is the barometer. What's the function? It measures atmospheric pressure. it measures atmospheric pressure. Their uses: it assists in altitude detection for GPS applications. It also enhances weather forecasting capabilities. It assists in altitude detection for GPS applications as well as enhances weather forecasting capabilities. Number 10, heart rate sensor. Heart rate sensor. What's the function? It measures heart rate using optical sensors. It measures heart rate using optical sensors. How about the uses? It monitors heart rate during workouts and throughout the day. It also integrates with health and fitness applications. It monitors heart rate during workouts and throughout the day. It also integrates with health and fitness applications. Let's now move to microcontrollers in mobile phones. Microcontrollers are essential components in mobile phones, controlling various functions and enabling communication between sensors and other hardware. Here's how they work. Number 1, functionality. Microcontrollers are small, low-power computing devices that integrate a processor, memory, and input-output peripherals on a single chip. They manage tasks such as sensor data processing, control signal generation, and power management. They manage tasks such as sensor data processing, control signal generation, and power management. Number 2, integration with sensors. Microcontrollers interface with the phone's sensors to process and respond to environmental inputs. For example, when the accelerometer detects a change in orientation, the microcontroller processes this data and sends a command to adjust the screen display. Number 3, low power consumption. Microcontrollers are designed for low energy consumption, allowing them to operate efficiently in mobile devices without draining the battery. They often enter sleep or low power modes when the device is inactive, further conserving the energy. Number 4, real-time processing. Microcontrollers can perform real-time data processing, allowing for immediate responses to sensor inputs. This is crucial for applications like gaming, navigation, and health monitoring. They enable features like gesture recognition, motion tracking, and touch input detection. They enable features like gesture recognition, motion tracking, and touch input detection. Number 5, communication interfaces. Microcontrollers facilitate communication between various components in the phone, such as sensors, the main processor, which is CPU, and communication modules such as Bluetooth, Wi-Fi. They use interfaces like I2C, SPI, and UART to transmit data between components effectively. In summary, sensors and microcontrollers are integral to the functionality of mobile phones, enabling a wide range of features that enhance user experience and interaction, from basic sensors like accelerometers and ambient light sensors to advanced biometric and environmental sensors. These components work together with microcontrollers to provide seamless operation, real-time processing, and energy efficiency. As technology continues to advance, the capabilities and applications of sensors and microcontrollers in mobile devices will likely expand, leading to even more innovative functionalities. Operating systems and apps. The operating system and applications in mobile phones are fundamental components that define the user experience, functionality, and performance of the device. Let's have an overview of both aspects. The first, operating system. The mobile operating system is the software platform that manages the hardware and software resources of a mobile device. It provides the necessary environment for running applications and facilitates user interaction with the device. Number 1, types of mobile operating systems. For Android, the developer is Google. Description: It is an open source operating system based on the Linux kernel, widely used in various devices. It supports a vast ecosystem of apps available through the Google Play Store. The features: number 1, customizable user interface and home screen. Number 2, extensive app library with diverse categories. It also supports multitasking and notifications. Next is iOS. The developer is Apple. The description: it is a closed source operating system specifically designed for Apple devices such as iPhone, iPad, and iPod Touch. It is known for its smooth performance and security. What are the features? Number 1, seamless integration with Apple's ecosystem such as Mac, iCloud, and so on. Number 2, regular updates and strong privacy features. Number 3, high quality apps available through the App Store. Next is Windows Phone. The developer is Microsoft. And what's the description? It is a mobile operating system designed for Windows devices, featuring a tile-based interface. It is no longer supported, but it was known for its integration with Windows PCs. There are also other examples. Let's now consider the core functions of mobile operating systems. Number 1, user interface. It provides the graphical user interface (GUI) for users to interact with the device, including touch gestures, icons, and menus. Number 2, resource management. It manages hardware resources like CPU, memory, battery, and storage, ensuring efficient operation and multitasking. Number 3, security. It implements security features such as user authentication like passwords and biometrics, and data encryption to protect user information. Another function is networking. It handles connectivity options like cellular, Wi-Fi, Bluetooth, and GPS, enabling communication and data transfer. We also have app ecosystem. It supports the installation, updating, and management of applications through app stores such as Google Play Store for Android, App Store for iOS. Let us now look at applications. Applications are software programs designed to perform specific tasks or functions on mobile devices. They enhance the capabilities of the operating system and provide various services to users. Number 1, types of mobile applications. We have here native apps. The description: built specifically for a particular platform such as iOS or Android, using platform-specific languages such as Swift for iOS, Java or Kotlin for Android. What are the advantages? The first is that it has better performance and responsiveness. It also has full access to device features such as camera, GPS, and so on. Disadvantages: it requires separate code bases for different platforms, leading to higher development costs. Another type of mobile applications is web apps. The description: it is accessed through a web browser and built using web technologies such as HTML, CSS, and JavaScript. They run on any platform with a browser. Advantages: number 1, cross-platform compatibility and easier updates. Number 2, lower development costs. The disadvantages: limited access to device features and may not perform as well as native apps. Another type of mobile applications is hybrid apps. Description: it combines elements of both native and web apps. It is built using web technologies and wrapped in a native shell. Advantages: number 1, single code base for multiple platforms. Number 2, it can access some device features. Disadvantages: it may not perform as well as fully native apps. Let's now take a look at app stores. Mobile applications are typically distributed through app stores. The first here is Google Play Store. This is the primary source for Android apps, featuring a vast selection across various categories such as games, productivity, and utilities. We also have Apple App Store. This is the exclusive platform for iOS apps, known for its strict quality control and security measures. App development and frameworks. Developers use various tools and frameworks to create mobile applications. Number one here is Android Studio. It is the official IDE for Android app development. We also have Xcode. This is the official IDE for iOS app development. Number three, we have cross-platform frameworks. Tools like React Native, Flutter, and Xamarin allow developers to create apps for multiple platforms using a single code base. Let's also consider user experience and interface design, UX/UI. The success of mobile apps largely depends on their UX and UI design. Key considerations include: number one, intuitive navigation. Easy to use interfaces with logical navigation paths improve user engagement. Number two, responsive design. Apps should work well on various screen sizes and orientations. Number three, performance. Fast load times and smooth interactions are crucial for user satisfaction. Number four, accessibility. Design should consider users with disabilities, ensuring that apps are usable by everyone. In summary, the operating system and applications in mobile phones work together to create a seamless user experience. The operating system manages the device hardware and software resources, while apps provide specific functionalities and services. With a diverse range of operating systems and applications available, mobile phones have evolved into powerful tools for communication, productivity, entertainment, and more. As technology continues to advance, both the operating system and app ecosystems will evolve, introducing new features and capabilities to enhance user experiences. That would be all for now on operation principles of mobile phones. Thank you very much for watching.